Welcome to Milliken, and welcome to the very first of our Tech Talks. The Tech Talks in which we demonstrate and actually talk to people about the initiatives and collaborations that Milliken is undertaking with partners to bring the future a little closer and make us more ready for the future. Today's talk has two presenters. On my left, Tamsin Getafa, and I hope I say that correctly.
Perfect.
Tamsin is Chief Sustainability and Chief Commercial Officer at PureCycle Technologies. And on my right, Dr. Scott Trenner, who is Principal Scientist at Milliken. They're going to address you in turn and give you a view of what their activities are. Thank you very much.
So we're all here because we have a plastics crisis and we have a consumption of using too much carbon. So we need to bring solutions to both the plastics and also the amount of carbon consumed to make plastics. And so PureCycle is bringing a new technology, a new innovation into the market, commercializing dissolution technology where we purify polypropylene. I've brought samples to pass around of different medias of scrap polypropylene, from carpet to serviceware to curbside, where we've dissolved the polypropylene and filtered it and cleaned it to look like virgin material. So when we talk about the different technologies and different processes, we can now insert dissolution technology and purification. So on dissolution technologies, it does take a little bit more carbon than mechanical recycling. We've all been hearing the life cycle assessments of mechanical recycling as being 90% less consumption of carbon than virgin. When we hear LCAs out of chemical recycling, we have depolymerization, where it's breaking down the monomer. And then we have conversion technologies where you break down to the molecular level and rebuild the resin. Those take a lot more carbon than the mechanical. Dissolution falls right between that and purification. What I want to share about our LCA today, while it doesn't show as big of an energy savings as mechanical at 90%, we're at 79%. As I mentioned, we're going to use a little bit more carbon to do that. We also did our life cycle assessment on a fully loaded, baked assumption. We are not going to be commercial for another few months yet. And so everything we've done is based on the assumptions of our commercial lines and the electronics that we put in the kilowatt consumed. So we anticipate that it's going to be even lower once we are fully commercial, and we're not going to extract a 700 horsepower extruder at 100%, right? So I just wanted to share that as excitement for the future, that we can bring even better carbon savings. So you can see we have different formats that can enter in polypropylene. There's woven and non-woven polypropylene. There's rigid containers. And there's fibers like carpet and things like that. You can see in our kit, the very first sample is black showroom carpet from a conference that we recycled. All those inputs go through what we call a pre-processing system, whether we shred and separate the different polymers in mixed rigids that we see, or we take in a shred and agglomerate fiber or film. We put that into our system, and then we extract the oligomers and the organics and the odors and the dyes in our first step. And then we go through a mixing and acetylene tank where we remove the polyethylene component. So for example, if you compound polypropylene, you're a compounder, and you compound polyethylene into the polypropylene, we're going to remove that polyethylene. If you compound calcium carbonate or talc or any kind of filler, we're going to remove that in the acetylene tank. And then we go through one more process where we take out the dyes. So if we were recycling, let's say, BOPP film, the dyes are most likely going to come out in the third process. And then we come out with a perfectly clear polypropylene, as you can see. But then we also recycle the solvent over and over again. We also have what I call co-products from each of these processes. And so unlike other types of recycling technologies, we are actively working with agreements on each of these components. So a polyethylene calcium carbonate blend is going to go into making flower pots, as an example. Where our first one is going to go into a cement manufacturing facility as another. And then even the flower pot people are going to use the last component of the dyes just as a filler so that we can help us get to a zero waste system. We'll probably still have about a 10% waste in our pre-processing system that we're not going to be able to reclaim because people do still add paper and glass and grit and dirt to some of the bales of plastics that we see. So people have asked us about FDA. When we first built our pilot plant about 3 years ago, we were really focused on post-industrial supply. And when I say we, I was not part of the company. I'm the one who said, no, we have to run post-consumer. So all our trials have been done on post-industrial predominantly. And so we have conditions of use A through H, which is all the conditions you would want to use for polypropylene. But it's on post-industrial supply because that was the supply that we did all the submissions on. At the last 11th hour, we were able, because we had a program where we were doing stadium waste. So we're working with certain football teams. It's been announced, the Cleveland Browns, the Cincinnati Bengals for people from P&G, the Jackson Jaguars. We do all the recycling at their stadium, and we take that in. I wish we had labeled it as food grade packaging or serviceware, something more broad, so I could have had more things, but it's called stadium waste. We are now working on a trial right now on the curbside material, and we're running the non-FDA curbside right behind it. So we've already done a pre-sort, we've already washed it, and we're submitting that. So we hope to show that we can do the same as the PET recyclers and get approval on all packaging. And so hopefully that will be our next LNO. I say hopefully, we never know. I talked to you guys about the energy, and now I'm going to talk to you a little bit about our goals. Now, anyone who's been in recycling understands you have to have critical mass to be economical, right? Feedstock is going to be our biggest challenge. We're planning to run 1 billion pounds over the next few years in capacity. So everyone's, where are you going to get the feedstock from? And so hence, we're attacking things like going to sporting venues. We're working with other genres of supply, things like super sacks from recyclers that might carry the resin to the converter, and the converter wants to buy the recycle. And we're like, we'll trade you. We'll get you some resin from us if you give us the super sacks. And so we have different programs like that that we're working on. But none of those supply streams are at large volumes yet by themselves. So initially, when we make our resin, our goal is to blend. We're blending, and we've been doing this for a little over a year now in our pilot plant where we consistently make a 15 melt. When I see enough critical mass of a lower melt flow, or I see enough critical mass of a higher melt flow within the streams that I'm feeding and blending to run on a line consistently so that I'm not going up and down and changing out and cleaning out, then I will have those melt flows. And as I mentioned, our goals and our targets to do 1 billion pounds. So we have what's called lines, right? Individual lines, the capacity of each line. The first one starts at 107 million pounds of output a year. And then our second and third line that we've already broken ground on is at 130 million pounds of capacity. So again, I have to have the feed consistent for the melt flow of one of those lines to be the most economical in what I sell. So the real benefit of working with Milliken is that they can produce additives and impact modifiers and melt flow changers that can allow us to adjust the melt flow of the 15 melt lower or higher. So the good news is we have this great partnership. And with that, I'd like to turn it over to Scott. In fact, he can even talk about the fact that you've seen them at the booth and that we have samples of virgin, 100% PureCycle, and then 100% PureCycle with Milliken additives, and you can see the difference in what they can bring to us already with clarifiers.
Yeah, thanks, Tamsin.
You're welcome.
So one thing I'll point out is if you look at just their base material and compare that to a homopolymer, they actually get quite a bit better clarity. And a lot of that is due to the dissolution process and the removal of the oligomers and low molecular weight fraction that can cloud, and also some of the additives in there. And then obviously with NX8000 Eco, we're able to improve that clarity a bit. So together we've made a number of samples and even some commercial products that are shown here. So this EC30 case is a commercial product from Procter & Gamble. It's a dry washing
dispenser for dry shampoo.
Right. And then with various resins and blends. So Tamsin has an example of the EBM bottle that we were able to blow mold with 50% of a PureCycle resin, so 50% recycled content. And then we have some of these storage containers, caps and closures. And you could see that, even though there are thousands of polypropylene grades available, And some of them are very specific for hinge closers. You could see that the PureCycle material was able to make a hinge closer at 100% recycled content. So as Tamsin mentioned, we're really excited about this relationship, and our goal is to take that 15 melt flow or that single grade and push it into as many different property spaces as possible, right, to meet the demands and try to match properties of polypropylenes that are available in the market. So I'm going to walk through a whole bunch of data, so I'll apologize a little bit for that. But it'll start with the PureCycle control, that's the base material that's nucleated with a Milliken product. And we'll compare that to kind of a homopolymer in terms of property space. We have the NX8000 clarifier that we've added, and that'll be compared to a random copolymer because we're really striving for clarity there. We've added 10 weight% of a polyolefin elastomer to get more towards a low to medium impact copolymer in case that your requirements require some impact. We've added this Ultra Balanced Solutions 10359, so that's our nucleating package that's designed for high stiffness. NX Ultra Clear with NX8000, so that's a clarified high impact material. And then finally, another impact modifier comparison where we've added our Delta Max product to get to a higher melt flow for more thin wall injection molding type applications. So first looking at the thermal and processability of these materials. So on the left here, I have peak crystallization temperature, and then here are all the samples that we looked at. And I'll say that their base material with the Milliken nucleating package is about 124 degrees C, which is pretty common for nucleated polypropylenes. The two samples with the NX8000 are a bit higher at 130, and then also the same 125-ish for the other nucleated samples. When we talk about melt flow, so Tamsin touched upon their main grade is going to be a 15 melt flow. We got kind of a special grade, I guess, in this one, or a subset of that, where we started at a little higher, about 27, but essentially the changes in mechanical properties that we're talking about will be just the same with the 15. So we did see a little bit of a decrease in melt flow, and that's because at this stage we're adding all of our products via master batch. But I know when PureCycle starts scaling up, they'll have a nucleated package and then also a clarifier package most likely. So those materials will be 100% post-consumer content. They won't have the master batch carrier. And then finally, our Delta Max, which is designed to increase flow and impact, got us up to about a 37 melt flow. So in terms of optics, so some of these packages are designed for RCP comparisons and are designed for optics, some are not. So I just kind of gave a quick image here. So the ones that are circled in green are the NX, so those are the ones that are clarity. That's a picture I took. I'm not a very good photographer, clearly. So I brought out samples here so you could see what the actual materials look like. It's probably a little better to look at the clarity from the bottom because these have the Digimark Holy Grail invisible watermark on it, which clouds the sides a little bit. But, in terms of polypropylene clarity, I mean, it's relatively, it's exceptional. So in terms of properties, what I did instead of just randomly picking individual polypropylenes to compare properties, what I did was for the virgin materials, we took about 50 different spec sheets for either homopolymer, a random, or an impact copolymer, averaged those numbers and showed the ranges. Because really we just want to say that, the PureCycle material isn't comparative to the specific material or virgin material, but the properties fall in the appropriate ranges for what they're comparing to. So if we look at just their beginning material, keep losing my pointer. So that's the RPP. You can see that the flexural modulus is about 1400 megapascals, which puts it right in the range of a virgin homopolymer. Random copolymers, it's a little higher for the nucleated, so we're about 1500 megapascals, so quite a bit stiffer than a random copolymer. And then by adding the impact solutions, the polyolefin elastomers, you do see a decrease, much like you would see if you add rubber to a impact copolymer. In terms of tensile strength, so I have yield strength and elongation at yield plotted. Yield is in blue, elongation at yield at 4, or in orange. And just the starting material, again, yield strength is about 33 megapascals, which matches very well to a virgin RCP or virgin homopolymer. The clarified one, a little higher at 35, higher than the RCP. The impact modified at 30, 28 or so, in the same range as a virgin impact copolymer. So taking this one stream from PureCycle and adding the different Milliken additives, we really feel that we could tailor a solution to your individual needs to match what you're currently using in terms of virgin production. Finally, impact properties. So the material as received with the nucleating package is a little better than a homopolymer. So this is about 5 kilojoules per meter squared and a notch Sharpie at room temperature. The clarified sample is about a little bit lower, so at 4. But again, it's still in the range of virgin random copolymers. When we start adding the elastomers in both just the base elastomer and the Delta Max, you could see again, we're in that virgin ICP range. So, there's a little bit of a detriment, I guess, to adding the impact materials because you're not at 100% recycled content anymore, but you need to reach the mechanical properties in the performance space to make a product. So just to kind of summarize where we've been, and it's a really busy chart, but I think it's a good a demonstration of how we push the boundaries of a single material to meet multiple different packaging applications. So the black curve here is the PureCycle material that's nucleated. You can see when we add the NX8000, the clarifier, you can see that haze really decreases compared to where we start. And similarly with the max impact, you can see that haze is quite a bit better. If you need more processability, the Delta Max additive or some of our other Delta Flow master batches can give you the higher melt flow in this case. So there was one other topic that Rabe, their product developer, wanted me to touch on, and that's blending. So as PureCycle scales, they may not have the volume to meet 100% of your needs. Additionally, if we think about a 15 melt flow, that's good for injection molding. We can visc break that and make it good for TWIM, but thermoforming, it's not going to work very well, right? So you're going to have to blend a low molecular weight material, or even EBM. That EBM bottle, I think we blended with a 2 melt flow and then about a 15 melt flow with the PureCycle material. So just briefly, and all of this will be shared on PureCycle's website as well as ours, so you can get the data later. You don't have to take all the pictures, and I won't go through all of it. But PureCycle did an extensive blending test with a couple different homopolymers, impact copolymer, and an RCP. And just as an example, I'll show melt flow. So if thermoforming or a sheet extrusion was the application that you were looking for, they took about a little over a 2 melt flow homopolymer. Here's the 15 melt flow PureCycle material, and you could see at somewhere between 80-20, it's probably about 25 or 30%, you're still in the right melt flow range for thermoforming. And that 25% is important, right? Because lots of brands have the 25% recycled content. So while we might not be able to get to 100% right now, at least by 2025, and for some of those brand commitments, there's the possibility of blending to get to those mechanical properties. So this is getting to higher melt flow range. So this is blended with a 50 melt flow impact copolymer. And you can see that trend is relatively linear as you blend and meet the right melt flow specs. And then there'll be the data will be shared later. So I don't know, Tamsin, if you wanted to share the overall comments, final summaries.
Well, I would just say that I think initially we can help people get to their 25 to 30% recycled content rates in the time frame that they're looking for. We are expected to be commercial in the early part of 2023. We're turning the lights on in December. And I think also if you go to our website, quite often we post the pictures of the advancement of the commercial lines that we've been building. So, we would love to have a conversation about how we can bring solutions together on sustainability.
Yeah, so thanks, everyone. Thank you for coming out here and joining us today. I know it's a busy show, and we're all kind of going around in a revolving door of meetings, so we very much appreciate your time.
Absolutely.
Before you rush off, there may be some questions that you'd like to ask the speakers,
Absolutely.
in which case they'd be very happy to answer your questions.
Hi, thank you for the nice presentation. It's very impressive, actually. And I have one question about the MFI. Is it kind of the limitation, or was it a target? You know what I mean?
No, it was literally when we look at efficiencies of running the plant, We found that if we blend all the different feedstocks we have access to today, at the volume we have today, blending it to a 15 melt, we offer a consistent material.
Nice.
And then we also don't lose capacity by shutting down, cleaning out, starting
Right,
another
sure.
melt flow. But as I grow supply and I see a longer period of time that I can get a lower melt flow, like with the super sacks, the raffia tends to be a lower melt flow. When I build up the 130 plus million pounds and make that one line, then I will blend over here and still make my 15
Right.
melt and then
Makes
make
sense.
a lower. So it's really about economics more than
Right.
anything else right now.
Thank you.
Just to ask, in terms of your raw polypropylene input material that you get from stadiums and so on, do you find that your melt flow varies from batch to batch, depending on what polymer's been used? And do you do a little bit of salting before? Is this or is your raw polypropylene really a mixture of impacts, randoms, and whatever you can
It
get
is a
hold
mixture, and it has been consistently falling between a 10 and a 20 melt flow, really hovering between 12 and 15. Both, I just want to say, on the stadium and on curbside, and they're very similar. You have cups that are thermoforms and cups that are injection molded, and you have thermoform trays. We have been, and then there's cutlery. We have been, in order to be a partner with a major sports team, we've said the way to make it economical to recycle is to become a monomaterial serviceware supplier. So if you can imagine, we've got injection molded cutlery, we've got thermoformed cups, and we've got injection molded cups. Blended together is very similar to curbside. And curbside, it tends to run just a little bit on the lower, like 8 to 15 melt. So you can see that we still can hit the 15 melt flow as a consistent material with blending. The raffia material that we get in, it can be a 0.35, but it can also be a 16 or a 20 melt flow. And again, we find when we get the raffia in and we're blending it all the time, hitting that 15 melt is really easy right now. So ultimately, we hope for sorting in the future, if we need to for melt flow, for critical mass, for someone who wants to pay me extra money, our sort lines are infrared to start out with, IR scanning systems, and then robotics. So we invested in the robotics for two reasons. If we need to take a certain format and sort it out because of the melt flow, or if we need to target food grade. So we have those two things in our pre-processing. So I just want to share with you, I want to have the broadest conditions of use with the broadest supply, but I've planned for the worst case scenario to be able to still answer the needs of the customers.
Sounds very interesting. Thank
Yeah.
you.
To get it right, you're not dissolving any of the
Other material.
polypropylene.
Yeah, no, I'm dissolving the polypropylene.
Okay. So why does it then matter that the MFI of the incoming raw?
It doesn't matter for dissolving it. It matters for the finished product to the customer. That's the only reason it matters.
So-
I would say that dissolving can have its limitations, we think, if we went way lower than, let's say, a 5 melt or way higher than a 50 melt because of the design of the temperatures and the pressure that we have in our dissolution system. It would be like a process engineer needs to be ready for a big change and adjust that. We can still dissolve it, but it's not going to be as viscous or less viscous when we do without making some processing engineering changes to the process.
So you're basically not substantially shortening the chain length of the polypropylene as such.
We're not affecting the molecular structure of the polypropylene at all.
Okay. No,
We dissolve it like salt gets dissolved in water. Evaporate the solvent, water, and you're left with salt again. We don't change the salt.
No, then I'm probably misled with people are doing with polyester. So okay.
You are, yes. So depolymerization, a different story.
Yeah. Okay.
This is dissolution, so it's a little different. And I think there is some dissolution with PET. I'm not sure. I know there is with polystyrene, but a little bit different. We don't affect the molecular
All right.
structure of polypropylene. We affect the molecular structure of everything that's in the polypropylene because we don't dissolve it. So we're filtering that off.
So that's why the blending is so important. No, I
Yeah.
get it. Okay, thank you very much.
Thank you very much for being here, and I hope you have a very successful K show. Thank you very much.
Yeah, thank you.